So welcome, everyone. Good evening, good afternoon, and good night for those in different places. I'm Professor Anderson from the Institute of Computing here at University of Campinas, Brazil. This talk it's part of the series of an agreement that we have between the University of Campinas in Campinas and the Catholic University of Rio de Janeiro in the marvelous city of Rio de Janeiro, called Conexão Rio Campinas, which is Rio Campinas Connection. Today we have the honor to count with Professor Stephen Grossberg, author of this excellent book here, just recently launched. And he's gonna be here with us for about an hour. This is a Q&A session, so we are gonna ask him some interesting questions about intelligence and neuroscience and about his research over the past 30 years or so. And I'd like to let you know that Professor Stephen Grossberg is a professor of cognitive and neurosystems, director of the Center for Adaptive Systems, and also emeritus professor of math, statistics, and psychological and brain sciences and biomedical engineering at Boston University, so Boston City, United States. Since 1957, he has discovered neural network models that link brain mechanisms to mental functions, including basic equations that are still used today. So I was introducing you and thanking you for accepting. I would like to give the initial words for you, Professor. You have been very well recognized for your work, mainly with ART, adaptive resonance systems, right? And you mentioned that it can solve at least 17 problems regarding deep learning. So if you could talk a little bit about the ART research that you have been doing over the years. I think, if I'm not mistaken, since 1989 when you first launched it, right?
Well, not really. The first article about adaptive resonance theory was published in 1976.
76.
And yeah. And it built on even earlier work. I started, my first discoveries were made when I was a college freshman at 17 years of age. And I took introductory psychology. That was 65 years ago. So I've been working in this field for 65 years. And I got fascinated at the time with learning, because after all, what do students do? But we learn day and night. And so I became fascinated by how our brains self-organize during both childhood development and adult learning. And that work really led to adaptive resonance theory, because I was particularly interested in how we can learn so quickly without also being forced to forget just as quickly. The problem of catastrophic forgetting, which, you know, you mentioned deep learning and its computational foundation, backpropagation, to this day does experience catastrophic forgetting. It's built into its bones, as it were. And we could discuss it if you're interested. Anyway, that led me to introduce adaptive resonance theory, because it solves the problem of how we can learn quickly without catastrophic forgetting, what I call the stability plasticity dilemma. The plasticity, how do you learn quickly without losing the stability of your previous memories? And now I think it's fair to say that ART or ART is the most advanced cognitive and neural theory of how our brains learn to attend, recognize, and predict objects and events in a changing world. And I say it with some confidence, because by now all of the foundational hypotheses of ART have been supported by subsequent psychological and neurobiological data. And it's also provide principles and unifying explanations of hundreds of additional experiments, many of those data collected after the predictions were made. And you might say, well, why has it been so successful? Why isn't it just another model? You know, everyone has his model. And I think these successes of ARC are at bottom because I was able to derive it already in 1980 from a thought experiment about how any learning system can autonomously correct predictive errors in a changing world that's filled with unexpected events. Some of you are physicists, I understand, so maybe you know from the work of Einstein that he derived both special relativity theory and general relativity theory from thought experiments. And you don't just wake up one day and decide you're going to derive something from the thought experiment. It only comes to after you've already understood something so deeply that you could see that behind all that success, there are just a few familiar facts that are familiar to us all from daily life. And that's because they provide ubiquitous environmental pressures on the evolution of our brains in the case of adaptive resonance theory. And I was able to derive art from facts you all know and you can't deny, but when you put them together, just a few of them, and think logically about their consequences, you're led to adaptive resonance theory type models. By type, I mean there are variants of art as it gets progressively developed over the years. It's not a complete theory, just as many theories in physics are not complete to this day. Just think about string theory. But emphatically, I want to emphasize that nowhere in my thought experiment do you mention the words mind or brain. These are very simple facts about life. And so the art design principles and mechanisms are thus a universal solution to the learning problem of how you can autonomously predict, autonomously correct errors through learning in a non-stationary or changing environment. And that's why I call it the stability plasticity dilemma. Yeah.
And one question that I had is this. We've seen, especially in your book and the talk that you prepared, a lot of key cases of success for the ART, the adaptive resonance theory. And on the other hand, we are seeing a lot of students and companies using deep learning models. And one of the reasons is that they can go online and get one model that's already there and they just can plug in and run. So one question that I received from students is, what if they want to try art for a particular problem? Would they have this tool set like ready? And if yes, where can they go to start digging around with art?
Well, the answer is yes. One place is go online to our CNS Tech Lab webpage, tech.bu.edu, and then you could look to see our software there. For example, Gail Carpenter, who I've worked in for many years, and her colleagues have designed a variant of art that uses a minimum number of parameters, which could be used in multiple applications and has been. Now, I want to make something clear, though. If you look at my book, let me mention it again, because I wrote it for students. In addition to everyone else, I wrote it for the general public. It's called Conscious Mind, Resonant Brain, How Each Brain Makes a Mind. And I'll say a little bit more about the book in a moment, but it's a big book, but it's written to be self-contained and non-technical. It's written in a conversational style. When I say it's written for the general public, let me mention that I have friends who are a rabbi, a pastor, a lawyer, a social worker, a visual artist, a gallery owner. They've been reading the book. They don't know science. But why I mention the book at this juncture is if you go into chapter 14 and look, well, maybe I can get it out. Look at figure 14.2. Let me show it to you. I can get there if I don't get too distracted by my search. I already passed.
Page 5 to 17.
Maybe you could get to it before I can. Let's see, this is...
Which figure do you want? The one of the structure, the circuit?
Okay, I got it too. Let me show it. So here, you see
the
that circuit. So if you look here, it's hard to look here at ITA and ITP. This is for visual intelligence, and IT stands for infratemporal cortex, and ITP is the posterior part, and ITA is the anterior part of infratemporal cortex. So the point is that that is where art as a classifier exists. ITP can learn categories that are view specific and position specific. But by the time you get to ITA, you can learn invariant representations of objects that you could recognize from any position, orientation, viewpoint, distance, and so on. In other words, by the time you get to ITA in these two regions of the brain, this is a solution of how some people have defined the classical pattern recognition problem. But all the rest of the brain does other stuff. So deep learning, to learn invariance, it's very much like Fukushima's neocognitron. And I like Kunihiko very much, but you need multiple processing stages.
And a lot of examples.
A lot of examples, very slow learning, but moreover, to get into the deepest issues about it, backprop and deep learning are both nothing but feed-forward adaptive filters. There's no feedback at all. There's no attention. There's no automatic regulation of search or hypothesis testing or information processing. Art, on the other hand, is a self-organizing production system that naturally embodies all these things. And because deep learning is just a feed-forward adaptive filter, it's untrustworthy in the technical sense that it's not explainable. And I'll say why in a moment, but this be not explainable means is okay. Let's say you're using deep learning and you've learned it over God knows how many learning trials, and it hasn't experienced its second problem. It's unreliable because you might be training it for hundreds or thousands of trials offline, very slow learning where you have to present the same thing many, many times because the weights can only get very small changes of weight. Of course, to do fast learning, which technically means you go from your initial adaptive weight to its final value, the whole thing collapses. So it's untrustworthy and unreliable. And what explainability means is that, let's say you were lucky enough offline to train it up without catastrophic forgetting, and you put in some kind of input vector and it makes a correct prediction. Well, you have no idea why it made the prediction. if you're making a financial prediction or a prediction about healthcare decisions, and you follow that prediction of deep learning and it's wrong, you'll be sued for everything you're worth, because in court they'll say, well, why did you make that prediction? And you'll have to say, I don't know, because I don't know the basis on which it makes its predictions.
Exactly.
Now, what I mean by explainability is contrasted with what happens in adaptive resonance theory, because adaptive resonance theory has both bottom-up categorization and top-down attentive feedback until you don't learn until you get a resonance in which on every learning trial, which occurs incrementally in real time, which is something else deep learning cannot do, but we do it all the time, art discovers, not only based on similarity during unsupervised learning, but also based on predictive success during supervised learning. And you can have arbitrary combinations of unsupervised and supervised learning, no sweat. It discovers what I call a critical feature pattern. It discovers that combination of features which will predict success. They are the features that you need to pay attention to for you to succeed in that environment. And it's the critical features, not all the other junk, that go into the adaptive weights in the bottom-up filters and in the top-down learned expectations. And therefore, the whole thing is discovering causality. As you learn more and more, you start to incrementally discover until the learning stabilizes. While it's still dealing with non-stationary fluctuations, it'll continually incrementally learn without catastrophic getting. It will learn the causes of events. And if you had to explain why you made the prediction, you could go into the algorithm, look at the critical features and say, I am predicting this patient outcome because these clinical results and these tests, whatever it is, I give examples of that in the book, predicted that outcome. That doesn't mean everyone's infallible, but you have good reasons. And those reasons often supplement what a doctor might have noticed by himself or herself. And in fact, Gail Carpenter, who I've worked with for many years, and to be absolutely clear, we also happen to be married and she's the love of my life. So we do tend to work together well, but Gail has done many things I haven't done, and I've done many things Gail hasn't done. She has studied medical database prediction. She's also studied, by studied, I mean modeled and made predictions. She's done this with people working in Boston area hospitals, and they've used it. She's also worked with NASA researchers to develop ways of classifying remote sensing data from satellites. And what's remarkable about these kinds of databases is, first, often the data is incomplete. Second, it often comes from multiple observers. Often these observers use very different labels, if it's supervised learning, for the same feature. So someone might call it a lake, someone might call it a pond, someone might call it water. Sometimes they make errors, often. In any case, so the data are incomplete, there are multiple observers, there are multiple, perhaps conflicting labels. And Gail has shown how art systems can resolve all these ambiguities to convert this information into knowledge. In fact, she has shown how an art map system can learn a cognitive hierarchy of rules. So it automatically stratifies the data in terms of its generality, and it gives probabilistic links that this implies that with a certain probability, that implies that. So you have an explicit if-then rules, fuzzy if-then rules, actually, if you studied fuzzy logic, a la my old friend Lotfi Zada, fuzzy if-then rules of the database. You have a completely transparent explanation, if you will, of the data.
And let me play the devil's advocate role. We've seen the importance of the art models in different applications. I have a question here in the chat from Professor Romangio. He's saying that he just today got to know this theory and he's going to look at it. So why do you think, as you have these many positive aspects of art, why do you think deep learning models like got more attention in the past few years than art models? You think it's like because it requires some knowledge in terms of neuroscience to be implemented or something?
No, you don't need any knowledge of neuroscience. Like if you look at the ART1 algorithm, it's just equations. No, and in fact, within the community of people in the neural network world, everyone knows art. The world we live in now, in so many ways, is fragmented, with different people learning from different traditions. So one reason, well, let me go back to backpropagation itself. Those of you who know a little bit of the history might say, well, that was discovered by Rumelhart, Hinton, and Williams in 1986. And the answer is no, it wasn't. Shinichi Amari already had a version in 67. Paul Werbos had a version that was really the modern version in 74. Paul did it as part of his Harvard PhD thesis. I know this very well because I was a professor at MIT at that time, and no one in his department would pay any attention to the algorithm. They didn't want him to get his PhD, and he asked me for advice, and I said, well, you just have to work out examples. So we did simulations with it, but this was in 73, 72, 73, 74. You know, computer simulations were a very different animal at that time. Computers were very different. You know, you didn't have a supercomputer in your pocket. You know, you had to go to a computer center and, you know, you had cards with holes in them and the whole rigmarole. Anyway, and so Paul got his PhD thesis. And then David Parker did more work on it a few years later. And Rumelhart, Hinton, and Williams knew all this background, but they choose to assert priority subtly. In other words, it was a case, not to put too fine a point of it, on a plagiarism. But remember, the foundations of backpropagation go back to Gauss in Germany. It's a form of steepest descent. It's a classical idea, steepest descent. You try to keep going closer and closer to the last data with your weights. And the problem is, how do you avoid drifts in the data, like with non-stationary data, sucking all your weights to the most recent exemplars? And art solved that problem. And the trick is to use the top-down matching by attentive feedback, and to make sure you get a resonant state, a consensus between bottom-up adaptive filters and top-down expectations, because before you incorporate new feature patterns in to categories you already know. So you're refining them, and you're suppressing unmatched patterns the top-down attention in art, the matching obeys what I call the art matching rule, and we can discuss the simple kind of circuit that realizes it. And by suppressing outliers, you solve the catastrophic problem. Well, maybe I'll say what the art matching rule is. Very, very simple. You have a top-down excitatory on center. You have a category. It's trying to turn on feature patterns at a lower level by reading out a learned prototype or critical feature pattern. That's excitatory. Well, you don't want to turn it on all by itself unless you want it to, unless you volitionally want to turn on internal thought into internal conversation or a spoken phrase. So in addition to reading out this top-down excitatory critical feature pattern, you're also reading out a larger inhibitory off surround. So you have excitatory inputs and inhibitory inputs all converging, but the inhibitory off surround is broader than the excitatory on center. It's called an on center off surround network. It's everywhere in the brain, and it solves a different fundamental problem that I've called the noise saturation dilemma. So if you look within the set of cells that are getting excitatory and inhibitory inputs, I can't do this with my hands. It's very confusing. You have more or less one against one. You might have a slightly stronger excitatory signal than inhibitory signal, so you can prime or sensitize the cells that you wish would fire in the on center. In the off surround, all you have is inhibitory suppression. And so well, let me just finish this thought, please. At that point, you've just primed the on center. But now if you have bottom-up feature pattern that partially matches that top-down prime, the cells where the top-down excitatory prime and the bottom-up features converge, they will fire, and that will start to form an attentional focus, and that will then activate a resonant loop, and they will be incorporated into the emerging categorical information. Okay, yeah, what were you going to say?
I was about to ask you this. So art seems to update.
One more thing. The art matching rule has been supported with anatomical, physiological, biophysical, biochemical data. It is there. And in fact, we have, since 1999, I and my colleagues have developed laminar cortical models of how the neocortex is organized. You know, the neocortex is organized very often, at least in perceptual and cognitive neocortex, in 6 characteristic layers. Why that is true and how the art matching rule is embodied in it. And that's all been supported by multiple physiological, anatomical, biophysical, et cetera, experiments. So what I'm telling you is not a metaphor. It has been verified on multiple levels. Yeah, sorry for being so wordy.
No problem. I have 2 questions regarding this. The first one is, art seems to update the learning with one example of a time. Each time you have one example, you update it. Differently from deep learning, which you have like a batches. So I would like to know something about the outliers in this case. What happens if you have outliers in the data set?
Let me restate what you just said. Batch learning is offline and it's supervised. We learn usually incrementally in real time. We have one experience at a time. That's how art learns. So having a batch isn't a good thing. That's what you do if you can't do incremental learning. Remember, if you have a self-stabilizing algorithm like art, I don't have to keep track of it even when it's learning in an unsupervised way. It will dynamically stabilize its learning based on similarity. And then you might say, well, how do you define similarity? And there's a lovely, really quite a beautiful story in what's called vigilance control. And let me just give you one example of vigilance control. You know, maybe I can do this right. Let me just draw a picture. Pictures make things so much easier. So let me, do you see these letters?
Yes.
On the left, that's E. On the right, that's F. In between, not so clear. So there's going to be a category boundary between E and F. And depending on how you define your fonts, that intermediate thing could be classified as an E or an F. And so let's say I thought the middle thing was an F. And I say to my teacher F, and my teacher says, "You idiot, that's an E." Okay, well, what happens then? Well, it's an unexpected event, and it drives a memory search for you to pay attention more closely to that letter to try to better understand what features in the letter you hadn't really attended to enough. For example, I could do the same thing. I show you a picture of a dog, and you know, I ask you, what is that? You say it's a dog, and I say, no, it's a Dalmatian, but that's a dog. And no, it's an animal. Well, that's a dog. And no, that's my dog Spot. Well, you have to be able to learn all those things about that picture. So you're going from one picture to many kinds of knowledge about it. That's a one-to-many map. Deep learning or many algorithms learn many-to-one maps very well. You look at pictures of different kinds of fruit, apple, pear, orange, and you look at all those pictures, you say fruit. That's many pictures of fruit, one name fruit, many to one. Anybody can do that. Whether you can do it without catastrophic forgetting, it's another matter. You can't do that with backprop and deep learning because it's based on mismatch learning. And when you put in the Dalmatian answer, it's going to force remapping of the dog weights. Well, that doesn't happen in art. So art can learn expert knowledge because it can learn one-to-many maps. And that is how Gail Carpenter and other colleagues, and myself included, can learn databases about remote sensing, medical databases, and so on, where you really need to know a lot of things about individual events, in addition to putting together many things into a prediction. So vigilance control, to summarize that, is at the moment of the unexpected event, and I say, no, wrong. What happens is a parameter called vigilance goes up just enough to drive a memory search to discover a better matching category. And there are theorems that Gail and I proved showing that it works. But you might say, oh, but that's, it's just a hypothesis, just a theorem. Not at all. After many years, my graduate student, Max Versace, and I showed how vigilance control is controlled in our brains. You can get, for example, a mismatch in the nonspecific thalamus. It activates the nucleus basalis of minor. The nucleus basalis of minor sprays acetylcholine, which is a neurotransmitter, into layer 5 of lamina cortical tissue. And due to the internal organization of our lamina cortex that drives the search, which increases vigilance enough to correct an error.
Okay.
And so, and that we made predictions based on that have all been supported by subsequent neurophysiological and anatomical data. But more to the point, you might say, oh, things get finer and finer, but what are you doing? You're spinning your wheels? No, because based on that understanding of vigilance control, I could begin to understand how one of the things that breaks down in a number of mental disorders, including Alzheimer's disease and autism, among others, are due to breakdowns of vigilance control. There are known problems in the nucleus basalis and in cholinergic metabolism. So that led me into a whole wild ride into trying to better understand the neural mechanisms of mental disorders. And you might say, well, oh, but does anyone pay attention to that? Well, let me give you one example of how they pay attention. In 1999, I think, I was invited to give the opening keynote address at the International Conference on Schizophrenia Research, which was held every 2 years. So for a theorist in 99 to give an opening keynote about predicting what goes wrong in certain schizophrenics, well, think about that. And my predictions already explain enough data for the experimentalists who are the big experimental clinical schizophrenia center in Maryland to invite me. Those predictions have held water as more data have come in. So this is very serious. So let me make a philosophical comment for the students. Be true to the fundamentals of what you're trying to understand. If you can just do that extra hard work until you begin to understand the underlying design principles, you will be paid off royally. I call it the gift that keeps on giving. I am still working, making discoveries 65 years after I started as a kid, probably your age, because I was true to the principles that I discovered. I wouldn't take shortcuts. Deep learning will hit a brick wall just as backprop did. You may not know that. Backprop became popular again in the 80s because Rumelhart, Hinton, and Williams would go running around to everyone saying, this is how the brain works, you know. This is the most important thing since God knows what. And then people started using it, and they still use it today. But then they stopped using it because of the catastrophic forgetting and the unexplainability in a lot of applications where it just was not okay. And they started using other methods like support vector machines and so on. And art has been used continually in large-scale applications. It's used in hundreds of companies. In fact, quite a few years ago, I was giving a lecture about art at a conference, and a guy came up to me at the end, and he said, I just want you to know that you're protecting the nation with art. He was from the National Security Agency. And of course, he couldn't tell me anything else. And in companies, intellectual property, they don't go around marketing. Oh, I'm so
Exactly.
wonderful. Look at my algorithm. Look at my application. They do the opposite. They don't want you to know. They don't want to lose their intellectual property. They don't want to lose their competitive edge. So Jeff Hinton, who's a very bright fellow, I met him when he was a student at UC San Diego. You know, they promoted backprop to the sky and then it collapsed. Well, why did it come back as deep learning? Well, it came back because two things happened in the interim years. One is that the internet happened. And with the internet, suddenly anybody could search for millions of pictures of cats. And the second thing that happened is that computer networks became blindingly fast. So you could feed millions of pictures of cats into an incredible network of computers that even today would fill a room, and let it grind and grind and grind until it had slowly, on many thousands of presentations of each of those poor cats, learned that database. And then you put in a picture of a cat, and out comes the prediction, cat. Wonderful. Gail Carpenter and I showed that R can learn whole databases in one learning trial, one fast learning trial. So when we saw this stuff, we were astonished by how excited people were getting by the hype. Well, I've been too busy making discoveries to do that, but you ask anyone in the neural network field who I am, and they will probably know. Even now, during COVID, I've given keynotes over Zoom at international conferences centered all over the world: Ankara, Beijing, Baghdad, Melbourne, London, New York, San Francisco. I can't keep them all straight, maybe 20 some odd countries just in the last couple of years. And that's because there are a lot of people who know about this work. So if you haven't known about it, I hope I stimulate you a little bit to look at it. It's there. And because of my magnum opus, which I wrote for a general audience, you can learn a lot about it. And then you could go to my webpage, which is sites.bu for Boston University.edu for education /Steve G, STEVEG. And if you want, you can read over 550 archival articles that prove everything that I try to make clear in the book and things I couldn't include.
That's very good. I would like to make two comments here. One is, the two are curiosities. Many of the cases of success of art that I could read, and some people are commenting here as well in the chat, work very well for tabular data. You
froze. I'm sorry. You froze on my end. Did I freeze on yours?
Am I back?
Can't. Your picture is not changing. Maybe you should start it again.
Okay.
Oh, okay, good. Yes,
yeah.
Thank you.
Okay. So the first thing, Professor, is do you have cases of success of art for images other than tabular data? This is the first question. And the second is a question from a colleague in the chat as well.
The answer is yes. First, Gail's work on remote sensing, those are images, for starters. But depending on how you define image, all feature patterns are images on a certain level of abstraction. But I've worked with various students, Jim Williamson, Gary Bratsky, Young-Chang Chow, on classifying image databases, and those papers are on my webpage. So yes, and in fact, we've, in order to speed the processing, of course, one of the issues that comes up with a feedback loop, people would say, well, how the hell does it run fast enough? Well, maybe I should comment a little bit on that. For example, if you know the work of Simon Thorpe, a very fine brain scientist in Britain, or Simon in Scotland, I forgot. I visited him, but I forgot. He shows that if you present familiar image there's a very fast feed-forward sweep through multiple cortical areas, leading to rather a fast classification of the image. So you might say, well, where the hell is the feedback there? Isn't DART too slow? Well, the answer is no. In fact, when data become familiar, you'll get a fast feed-forward sweep through multiple cortical areas, and the ART feedback just confirms that sweep while you're recognizing it. So you might have activated the cells that predict the right answer within, I don't know, I can't remember the numbers, 20, 40 milliseconds. And it might take extra milliseconds for you to consciously be aware of your classification. That's the time it takes for the ART resonance to take hold. The feed-forward sweep and the confirming feedback, no sweat. But for conscious recognition, it often takes 100 to 300 milliseconds. And that's why, when you think about our understanding each other in language, which I've studied speech and language for many years also, I love the topic, of course. Our hearing, our conscious hearing of what you're saying, the sound from your voice hitting my ear, I won't consciously hear it for maybe 100 or 200 milliseconds. So we're all always lagging each other. So all of these lag effects are very interesting, but our legs are, pretty synchronized, so we never noticed it. So, and it takes a different amount of time for me to consciously see you than hear you, but that is all resynchronized. And with my student, Alexander Grunwald, we studied data about what's called conceptual framing, how our brains resynchronize data that's processed at somewhat different rates within a synchronization window. And that's why we have these waves that are synchronizing.
I'm not sure if I'm gonna say something that's very wrong here, but is this the reason that some people say that we live in a state of simulation? Because as you have the lag because of the audio and the visuals, and then you need synchronization in the brain. Some people say that we are kind of living in a matrix, or I'm completely out of.
Well, I love the matrix, but I don't think we're quite living in the matrix, because that was a total simulation, including the characters. No, more to the point, think about what an image from a scene in the world looks like when it hits your retina, your photosensitive retina. Now, you may or may not know the following, and if you do, that's fine. My book discusses it vividly. I can't find the images in real time. That our retina has many, many photosensitive cells, and the signals that it creates are bundled together to go up the optic nerve into the brain. And there's so many pathways or axons that have to be bundled together that the optic nerve is pretty wide. And at the place on your retina where all those signals are bundled together, you're blind. It's called a blind spot. And I can explain in a moment why you're not aware of that unless you do the right thing. And where you are most visually sensitive is another part of the retina that's called the fovea, F-O-V-E-A. And remarkably, the blind spot where you can't see a thing is just about as big as the fovea where you do most of your vision. And you're not really thinking too much about that. But the reason that your eyes move all over, several times every second with saccadic eye movements is to point your fovea at the things you want to look at, because otherwise it's a bit of a blur in the periphery. So, and moreover, your retina is metabolizing at an incredibly fast rate. It needs to be nourished. So coming out of the blind spot is this web of retinal veins, which happen to cover the photodetectors that would have been there. So they're not. So not only do you have a blind spot, but then you have this web of regions which don't get any signal. So if you want to talk about a simulation, the simulation is how do you go from that? Also, there's blurring and smearing because of the properties of the lens and the vitreous fluid. How do you go from that smeared out, incomplete, noisy image into seeing my face? Where's the hole? Where are the veins? That takes multiple stages to construct from that incomplete, noisy image a sufficiently complete, context-sensitive surface representation that's worthy of planning actions based on it. If we use the early signals, they're so noisy. If we planned our actions based on that crap, we'd be dead. Darwinian selection would wipe us out. And so we need all these stages to build boundaries and surfaces and compensate for variable illumination. Well, how do we know what stage gives us a complete enough surface representation to act upon it? I predict it occurs in pre-stride cortical area V4. V4 means there's a V1, a V2, a V3A, et cetera before. There's also the lateral geniculate, before that the retina. V4 is where the surfaces are finally good enough. Well, how do we know that we should choose the V4 representation? Well, the prediction is that the next processing stage, posterior parietal cortex, which is known to be important in spatial attention, meaning feeding back to V4, and movement intention, meaning feeding forward to action. It's an interface between spatial attention and action. Parietal cortex, PPC, and V4 resonate in what I call a surface shroud resonance. The shroud is form-fitting spatial attention that lights up the surface representation, and we consciously see that. So,
but it takes some time, right?
Let me make conscious seeing occurs in order to select sufficiently complete surface representations on which we can base successful eye movements and reaching movements, etc. And it does take time. Yes.
Yeah.
And those
exactly because
those times have been measured. Yes.
Very good.
It takes. Yeah. We're always lagging. Hundreds of milliseconds behind. So keep in mind, though, conscious seeing is going on toward parietal cortex and up into the cortical ware stream. That's the dorsal part of your brain. That's where you have space and action. Conscious recognition, what classical art does, is in the ventral part of the brain, through infratemporal cortex and up to prefrontal cortex. So it's when the feature category resonances in the ventral part of the brain and the surface shroud resonances in the dorsal part of the brain synchronize. In that moment, you can consciously see something that you know about, but it is pretty much whole brain resonance. It's using, And you might say, well, why do you need so much brain? Well, I already gave you an indication a moment ago, and then I'll shut up after I try to clarify this. Remember, you don't want to have a combinatorial explosion of information. I don't want to have a different output pathway for every viewpoint or size or position of your face. I want to learn a view and position in variant representation. And as I said, we know you do it by the time you get to anterior infratemporal cortex. But if you're going to be using that positionally invariant representation, okay, let's say I know it's you, but then how do I act on that knowledge? How do I look at you? How do I move to you? For that, I need the very spatial information that I just worked so hard to get rid of so I can recognize you in an invariant way to solve the combinatorial explosion problem. And that's where you have what to where interactions. So you get your cake and eat it too. So I can recognize you in an invariant way and then know where you are and look at you and act on you. And I explain in my book how to do that. And that's all about adaptive coordinate changes. None of this bullshit and just having a homogeneous series of backpropagation or deep learning layers. It's not how it works. You can't do anything
very
important with that.
I have, we are approaching the end here. I have one or two last questions and you can summarize. So one is...
well, before that, I want to say one more thing. Mm-hmm. My book is almost 800 double column pages with over 600 color figures. That's because I wanted to be able to say a lot in it in a way that anyone could read. It would have cost well over $100. But why work so hard on a book for everyone if no one can afford it? So you'll notice that if you go on Amazon today, at least in the United States, it's been discounted from the price of $35 to $33.50, I think $33.25, and the Kindle version is only $19.
Yeah, it
okay,
was only
the
32.
Kindle version is only, and the reason you only paid that is because I gave the publisher many thousands of dollars to subsidize you. So I want you, if you're interested in how brains make minds, to please consider looking at the book while I'm alive. And if you want to ask me questions, I'm just steve@bu.edu. And I'm going to brag a little, forgive me. You know, I'm an old man, you know, I'm going to brag. In 1989, I think it was, I was invited by the president of Boston University, who was then John Silber, who was notorious as a very tough guy, to give the annual university lecture to the general Boston area audience. And John got up and he introduced me in a way that I almost thought I'd faint, because he called me even then the Newton and the Einstein of the mind. And I've made so many discoveries since, including how and why and where we consciously see, hear, feel, and know things about the world, and can use conscious representations to plan and act to achieve valued goals. So, you know, if you want the magnum opus of the Newton and the Einstein of the mind, I subsidized it for you. So get it for $19 on Kindle.
Thanks a lot. And the book is really great. I have the hard copy. That's why I paid $32. Thanks for subsidizing. It's great. I totally recommend it. Professor, one last one. Art is a really good theory and works well in practice. Danielle here is asking, based on your experience, especially with ArtMap, do you consider to be the most, what do you consider to be the most distant from the real functioning of the biological brain? I mean, if you consider art on one side, which part of this theory is the most distant from what's really happening in the biological brain?
Well, first, please don't only focus on art. It's a classifier. That's the small part of our intelligence. That's why I showed you figure 14.2 in my book. Mm-hmm. Remember, I told you about my thought experiment in 1980, where I showed that if you do a thought experiment about how any system can autonomously learn to correct predictive errors in a non-stationary world, you're led to art-style systems. By that, I mean that all of them will share some foundational components, like an attentional system, an orienting system, top-down attentional matching, predictive disconfirmation leading to hypothesis testing and search. But the embodiment of these will often depend on your application. So for example, some of our colleagues, some of the best chip designers in the world, and they tried to design kinds of analog chips that would embody art so it could run in real time in hardware. But at that time, sorry, I just have asthma. The chip design just wasn't up to the task. But art was run in uber fast ways on pipeline systems and other ways. Then you could do variants of art that do run in real time because you really strip down the dynamics to the bare bones. Gail did that with default art map, and I did it with Gary Bradsky with a model we call Cortex. So all of them incorporate foundational design principles and mechanisms, but the way in which you implement it will depend on things like what computers you have. Like when we first started this, many years ago, computers just weren't up to the task. I remember when I was a PhD student at Stanford University, between 61 and 64, before a lot of you were born, I had made some basic discoveries about the foundations of how our brains work. And Stanford at that time had the top computer simulation lab in the country. And my advisor said, go over to those folks, because at the time I couldn't prove anything about them. And I only had my intuitions about how it must work. Since then, I have proved these theorems, but I couldn't then. And I brought the systems to them, which are nonlinear neural networks. And because there's learning and activation, there's a fast time scale and slow time scale. And at that time, they couldn't simulate it. Their computer just couldn't do it. But then, now we have computers that can do massive art simulations, much more complex systems. It depends on your simulation environment. So times change depending on what tools you have to implement ideas. And whenever you're implementing fundamental theoretical work, you're always making design choices. And that's why it's really important for you to try to understand what you're doing. Now with deep learning, because it's just a feed-forward adaptive filter, there are no design choices.
Exactly.
So,
Professor.
So yes, yeah.
So to finish here, I would like to ask you, with your 50+ years of experience, what would be your key advice to the students that are following us today, and will do it online later, if they want to really pursue machine learning? differently than just getting the latest hype and using it?
Okay, well, first, I think one should make some meta-theoretical comments. It's one thing to get a degree, whether it's a bachelor's, a master's, a PhD. In that case, these are often pragmatic decisions. But it's also the case that the pragmatic decisions you make put you on a path to getting jobs, and that path can lead to the rest of your life. So these are important decisions, this combination of politics, intellect, and knowing the world you're going to be living in afterward. But to me, it seems the most important thing, modulo all this, is try to find problems that you're passionate about. Because if you're going to try to solve a problem that's worth solving, you're going to have to put in a lot of work. And if you don't really give a damn about the answer, why bother? Just go into business and make as much money as you can and settle down and have a wonderful family life with your children and your hobbies. You know, going into, or, you know, if you're going into technology, they're going to tell you what to do. And so the best thing to do is to get the broadest technical education you can. So with our PhD students, we had very gifted students who were attracted to our department. We try to give them a very broad and deep modeling and technical education. They all had to take 18 graduate level courses. Some of those courses included stuff we've discovered, but many of them were just trying to explain to them what the world outside looked like so they could be qualified for the job they wanted. And they got snapped up, whether it was for a neuroscience job or a company job. They were snapped up because they had really good fundamentals and broad knowledge. So try to be as versatile and as broad as you can while following your passion. And knowing enough mathematics and computer science in our age is really useful. Mathematics is the queen of the sciences for a reason. And it's really important even for the design of computer systems. Like BU has had some of the world's most famous computer designers who were trained as mathematicians. So get a good foundation and don't fall to the hype. You'll hit a brick wall when you're much younger than you want to be. As I'm saying, you know, I've been riding this wave for 65 years, and one discovery laid the foundation for the next and next and next. I never thought people would actually listen to me lecture about music and art. I mean, come on. But it sort of came out of the wash, among other things, or mental disorders. So my trajectory isn't yours. It's a different world for you than it was for me. But similarly, you get the foundations right, the gift that keeps on giving may, you know, surprise you.
Thanks a lot. Very good conversation. I wish you all the best. Thanks a lot again for being so kind and accepting to talk to us, and to the audience.
And
also, thank you.
Read my book.
We will do it. Thanks a lot, Professor.
Okay.
See you.
My pleasure. Bye-bye.
Bye-bye.